So this is very simple example to illustrate the torque of a force about a point. So this is point A. So this is just Cartesian coordinate axis. So this is point A. There is a body. There is a body. So this is a body, rigid body. At point A of this body, this is a rigid body. At point A of this body, a force, that is this force of 2 Newton is exerted. Coordinate of point A is 2, 1. Coordinate of point A is 2, 1, and this force makes angle 45 degree with horizontal or with respect to this x-axis. So this is x-axis, this is y-axis. So force makes angle 45 degree with x-axis. We have to find torque of this force F about this point O. For simplicity, we have taken this point O. That means if we fix this body, if we imagine that this body has been fixed at point O, it is not able to move, but it is free to rotate about point O. Body is free to rotate about point O. Then torque of this force F about point O will be rotational tendency of force F about point O. We have just, this is the force, so we have extended the line of force. So this is the line of action of the force. This dotted line is the line of action of the force. To find the torque of this force about point O, we have taken an arbitrary point B. Arbitrary point B on the line of action of the force. So this is point B. For simplicity, we have taken it here. We can take it here or here or here, anywhere, but that will be quite complex. So for simplicity, we have taken a point on the line of action of this force at this point, that is intersection of x-axis and line of action of the force. So this is the point, and position vector of point B with respect to point O is OB, that is R. Position vector R is OB, that is position vector of point B on line of axis of the force, line of action of the force with respect to point O, about which we have to find torque of the force. So first method to find modulus of torque is force into lever R. That was our first formula. Here we will just denote force, that means magnitude of force. Similarly, we can write it torque, that means magnitude of torque. So magnitude of torque is equal to magnitude of force, absolute force, into arm of lever or arm of moment, that is perpendicular distance from O to line of action of the force. Perpendicular distance, that this is the point O, so perpendicular is this. Let this is point C. So OC is the perpendicular distance from O to line of action of the force, and OC is arm of lever. So arm of lever is OC, and OC is equal to OB into, OC is perpendicular distance from O to line of action of the force. So OC is OB into, let this angle, let us find this angle. So this angle is 45 degree. So you can say this angle is also 45 degree. This angle is also 45, hence this angle is 45 degree. So both these angles are 45. This angle, So this angle is 45 and this is 90, hence this angle is also 45 degree. So OB into sine 45 degree. OC is OB into this angle. This angle is 45 degree. B point is 1, 0 coordinate. So OB distance is 1. So 1 into 1 upon under root 2. That is 1 by root 2. So arm of lever is 1 by root 2. 1 by root 2. So you can say torque is equal to force into arm of lever. Force is 2 Newton into arm of lever is 1 by under root 2. So it is under root 2 Newton meter if x and y coordinates are given in terms of meter. That is, distance taken along x axis and y axis is measured in terms of meter unit. So it will be Newton meter, under root 2 Newton meter. So this is our first result. T is equal to under root 2 Newton meter. And what will be the direction? This force is trying to rotate the whole body about point A in anti-clockwise direction. That means positive direction. So anti-clockwise is positive. That means torque is upward from the board perpendicular to R and F, that is plane of this board, and towards the viewer, positive, and or you can say anti-clockwise. All are same. So this is the first method by finding arm of lever or arm of moment or perpendicular distance from point to line of action of the force. All are same. Now our second formula was T is equal to R into F perpendicular. That means position vector, modulus of position vector of any arbitrary point on the line of action of the force into perpendicular component of force F with respect to vector R. So R is vector OB. R is vector OB. So we can say this is also direction of vector OB. We can put this vector OB here also. So this is vector OB. So the angle between vector R and vector F is 45 degree. So component of force which is perpendicular to the direction of vector R is this, F perpendicular. So component of force F perpendicular on vector R, that is vector OB. We have taken the vector OB here. We can assume it. An angle between OB and F is 45 degree. So this component is F sine 45. F sine 45. So F perpendicular component is F sine 45 degree. F is 2 into sine 45 is 1 by root 2, that is under root 2. So this is perpendicular component of force on position vector R. Torque is R into F perpendicular. R is 1. Modulus of R vector is 1. Vector OB. So 1 into perpendicular component of force is under root 2. So this is under root 2. So torque is under root 2 Newton meter. So by this formula also we have found torque is equal to under root 2 Newton meter, and direction will be same. This is F perpendicular. F perpendicular will try to rotate body in anti-clockwise direction. So this is also positive. or anti-clockwise torque. So we have found torque of force F with respect to O, first by finding arm of lever, second by finding perpendicular component of force with respect to any vector R, which is position vector of any point on line of action of the force with respect to point O, about which we are finding torque. Third method, as the general definition of torque is R cross F. That is, modulus of torque is modulus of R cross F. That is the general definition of torque. So by this general definition itself, we can find value of torque. We can write it like this: mod of R into mod of F to sin theta. Mod of R, that is vector OB, is 1 into mod of F is 2 into sin theta, that is, and theta is angle between R and F, which is 45 degree. So it is sin 45. You can write it like this: 2 into 1 by root 2 is equal to under root 2 Newton meter. So by its own definition, torque can be found as R cross F. R is position vector of any point on line of action of the force, and F is force F. So it is also, so that is the third method. We have found torque is equal to under root 2 Newton meter by its definition. So this has been found by F into arm of lever. This has been found by R into perpendicular component of F, and this has been found by modulus of R cross F. Fourth method to find the torque is by using right-handed unit vector system. Right-handed unit vector system, which is IJK, which we have discussed earlier. I is unit vector along positive x-axis direction. J is unit vector along positive y-axis, and K is unit vector along positive z-axis. So I, J, K are unit vectors along x, y, z positive directions. So by this definition, we have to find, we know the definition of torque is R cross F. So we have to find vector R and vector F in terms of I and J. So I is in this direction, unit vector in this direction, and J is unit vector in positive axis of y-axis, along the positive direction of y-axis. So R we can write as vector R. You can write as modulus of R to I. Modulus of R to unit vector I. Because R and I are in same direction. R and I are in same direction. Hence we can write vector like this. Vector R in terms of vector I. It can be written as 1I, that is I. So this is vector R. Now vector F. Vector F. This is vector F. To express vector F in terms of vector I and J, we have to find components of vector F along I and J. That is vector F. So x-axis, along the x-axis, let the component is fx. Along the y-axis, let the component is fy. That was also, we have earlier said it, perpendicular component of F. So vector F has two components, along x-axis fx and along y-axis fy. So Fx along x-axis, you can say F into cos 45. F into cos 45. And this is 2, 1 by under root 2, it is under root 2. Under root 2, that is the modulus of Fx. Similarly, mod of Fy, that is y component of force, is F into sin 45. That will be same, which is under root 2. So these Fx and Fy both are under root 2. So we can write vector F as vector Fx plus vector Fy. We can write like this because F is the resultant vector of Fx and Fy. Now Fx, vector Fx can be represented in terms of I because it is parallel to I. Fx is x component in x-axis, direction of x-axis. So vector Fx can be written as mod of Fx into I. This is vector Fx plus mod of Fy into j. This is vector Fy. You can write it like this. This is vector Fx and this is vector Fy. Vector Fx is mod of Fx into vector I because Fx is in the direction of vector I. Hence Fx can be represented in terms of I, that is magnitude of Fx into I. So magnitude of Fx into I. Similarly, Fy is in the direction of j vector. So Fy can be written as mod of Fy into j because j is the unit vector. So mod of Fx and mod of Fy are known, that is under root 2. Both are under root 2. So vector F can be written as under root 2i plus under root 2j. Now torque is R cross F. So R is I. So you can say R cross F is equal to vector I cross F is under root 2i plus under root 2j. And this is I cross I is 0 plus under root 2 I cross j. We have earlier discussed in vector chapter I cross j is k. So torque in terms of ijk right-handed vector system is under root 2 k. Under root 2 k. So by this method also torque is equal to under root 2 k Newton meter. Here k is along the z axis. So z axis is perpendicular to x and y axis and positive direction of z axis is towards the viewer. So the direction of torque is under root 2 into k vector. K vector is unit vector along positive direction of z axis. So these three vectors are also in direction, they are towards the viewer or upward from this board, and the same representation in the terms of ijk you can write like this, that is under root 2k. That also denotes that torque is having magnitude under root 2 and its direction is towards positive direction of z axis. Positive direction of z axis means it is anti-clockwise. By convention, it is anti-clockwise. So these are the four methods. One by lever of arm, force into lever of arm, that is force into lever of arm is perpendicular distance from O to line of action of force. Second, by position vector into perpendicular vector of component of F. That is, position vector is B, so OB, and perpendicular to OB is this F perpendicular, that is F sin theta. This is also under root 2. Third is by basic definition R cross F. So R cross F, mod of R into mod of F into sin theta, that is under root 2. Fourth is by unit vector IJK, which is right-handed system of unit vectors along x, y, z axis. That is under root 2k. That means under root 2 is the magnitude and k means in the direction of z axis, positive direction of z axis, upward from the board or towards the viewer, perpendicular to this plane, that is R and F vector plane. So all three torques are same, but their methods are slightly different. The basic definition of torque is about a point is R cross F. T is vector R cross vector F. Again I am writing is, this is the basic definition of torque of force about a point, where R is the position vector of any point on the line of action of the force with respect to point about which torque is being found. So again I am repeating, a force can be transferred along its line of action. It is acting at point A, it can be transferred at B also in the same direction. It can be transferred at C also in the same direction. That we will prove later. And the reason is, during this transfer of force along its line of action, the effect in all cases remains same. That is its rotational effect, torque, and its linear effect, that is linear acceleration. Both effects of force are same when it is transferred along its line of action. So by simple example we will understand how to find the torque of a force about an axis by different methods which we have discussed earlier, by general formula as well as by using special cases which we have discussed earlier. So in this example, this is x-axis, this is y-axis, this is z-axis. We are finding torque about this axis, that is z-axis. So about the z-axis, we are trying to find the torque of a force acting at point A. So this is a body, rigid body, under a rigid body. So here you can see this force is lying on xy plane, represented by x is equal to 1. That means this line is parallel to y-axis. This line is parallel to y-axis, perpendicular to x-axis. So this angle is 90 degree. Line is x equal to 1. We want to find torque of this force about z-axis. So here you can say this line is lying on xy plane and it is parallel to y-axis and perpendicular to x-axis. So this line of action of the force is perpendicular to z-axis. You can easily imagine this line of action is perpendicular to z-axis. So that is our first case. When force and axis of rotation both are perpendicular and line of action is not intersecting the axis of rotation because it is in the plane xy parallel to y-axis. So in that case, magnitude of torque was given by Rp is equal to into force, where Rp is the perpendicular distance between axis and force. Here perpendicular distance between axis and force is 1 because the intersection point at x-axis is 1, 0, 0. So distance, perpendicular distance, that is OB. RP is OB. This OB is perpendicular distance between axis and line of action of the force, which are perpendicular to each other. That is, force and axis are perpendicular to each other and not intersecting each other. RP is OB, that is perpendicular distance between axis and force. And force is 5 Newton. So torque is RP into force. Simple, that is 1 into 5, it is 5 Newton meter. If dimensions are in MKS or SI system, then it will be 5 Newton meter. Now this force you can easily see is in this direction. If you see from the top, it will rotate in anti-clockwise direction. It will rotate the body in anti-clockwise direction. That means direction of torque will be towards the pivot, that is upward, because you are seeing from top. Anti-clockwise rotation, direction of torque is towards the pivot, upward. So magnitude is this and direction in the positive direction of z-axis. In vector term, you can write torque is equal to 5K. You can assume I as unit vector along positive direction of x-axis, J as unit vector along positive direction of y-axis, and K as unit vector along positive direction of z-axis. So torque is 5K. This is first result. We will write our first result here. Torque is equal to 5K. Now we will find torque by second method, which is also very important to understand its concept. Example is very simple. You have to just understand the concept. Now we will find torque by finding components of F, that is force, along x, y and z direction. So if there is a force F, there is vector system, that is x, y and z. So this force can be divided in 3 perpendicular directions, that is along x-axis, this is called Fx, along y-axis, this is called Fy, and along z-axis, this is called Fz. Every force in 3-dimensional coordinate system can be divided in x, y, z direction, which are components as Fx, Fy and Fz in x, y, z directions. So you can write it as F is equal to Fx, x component plus y component plus z component. We can write it like this. So we have to individually find torque of Fx about the axis, torque of Fy about the same axis, torque of Fz about the same axis with directions, because torque is a vector quantity, either positive or negative, clockwise or anti-clockwise. And then all these 3 torques have to be added algebraically. Positive torques plus negative torques, and then we will find net torque. That net torque will be torque of this resultant force. This is a theorem which is called Varignon's theorem. So Varignon theorem says that the torque of a force about a point or axis is equal to sum of individual torques of its components about the same point or axis. So we can say torque of F about axis, that is axial component of R cross F, axial component. So this axial component is found by dot product of unit vector along the axis. and then putting the unit vector along the axis. So this is the axial component is equal to r cross fx, axial component of fx vector plus r cross fy, axial component of z vector fy vector plus r cross fz, axial component of fz vector. So this is called Varignon's theorem. That is, torque of a force is equal to sum of its component about the same axis or point. So in this case, F is given. Now we will break F in Fx, Fy, Fz direction. Fx, Fy and Fz direction. For this force, you can easily see Fx is equal to 0 because this is parallel to y-axis, so axial component along x-axis and z-axis are 0. Fx is equal to 0, Fz is equal to 0 and Fy is equal to F. This you can easily see here. So these are the components Fx, Fy, Fz of force F, this force F. Now we will find torque due to every component along the z-axis and sum all those three torques, and that will be equal to torque of this resultant force about the z-axis. So first of all we will find torque due to Fx. Now here you see Fx is component of F along x-axis, even though it is 0, but just assume it is non-zero, then its direction will be along x-axis. So the perpendicular distance between z-axis and Fx will be y coordinate of this point A. So y coordinate of point A will be perpendicular distance between axis and Fx, and y coordinate is 1. So perpendicular distance between Fx, that is component of F along x direction, and z will be y coordinate of point A, that is 1. So torque by formula Rp into F you can find. This formula is valid because here also force and axis both are perpendicular to each other. So torque is Fx into Rp is equal to 0 into 1 is equal to 0. So you can say this Tx. Tx is torque due to Fx, Fx into Rp. Rp is the perpendicular distance between Fx and z-axis, which is 1, that is coordinate of y coordinate of point A. So Fx is 0, hence 0 into 1 is. Similarly Ty. Ty due to y component. So y component is along the y-axis. It is equal to actual force 5 Newton. So 5 into this force is perpendicular to axis of rotation, and distance between axis of rotation and force, that is perpendicular distance between axis of rotation and force, is x coordinate of point A, x coordinate of this intersection point, or x coordinate of point A. X coordinate of point A is nothing but perpendicular distance between Fy and axis of rotation. So 5 into Rp, and here 5 into perpendicular distance is x coordinate, which is 1, it is 5, and this Ty is in anti-clockwise direction. Anti-clockwise direction. Now Tz is torque due to z component of F. Z component of F, that is along the z axis, and that is 0. So 0 into Rp. So we know the z component of force is parallel to z axis. So earlier we have seen in a special case that a force which is parallel to the axis will have 0 torque, because this Fz is parallel to z axis, hence torque of Fz about the z axis will be 0. So it will be Fz is 0, hence it will be 0. So the total torque, that is Tx plus Ty plus Tz, total torque is, you can write here, total torque is Tx plus Ty plus Tz. This is vector actually quantities. So add all these here. Tx is 0, Tz is 0, only Ty is non-zero torque. So Ty is 5 Newton meter, this is Newton meter, in anti-clockwise direction. That is, when we will see from upward, it will rotate in anti-clockwise direction. That means direction of torque is towards the viewer, that is positive direction of z axis. So total torque is 5 K. You can write it like this. Now we will find the torque by third method, which is with the help of IJK, that is right-handed unit vector system. So assume along the x-axis I, unit vector is I, along y-axis unit vector is J, along z-axis unit vector is K. Now this is the basic formula. We have to find R, we have to find F, we have to find N in terms of I, J, K. So let us take an arbitrary point on axis of rotation SC having coordinate 0, 0, 1, and another arbitrary point on line of action of force as A having point coordinate 1, 1, 0. So vector R is vector CA, vector CA, vector CA is achieved by so vector R is vector CA, that is position vector of A with respect to C. Now CA can be achieved by OA minus OC, that we have studied, that is position vector of A minus position vector of C with respect to origin. So vector OA, vector OA, vector OA will be, this is origin actually, so vector OA will be based on the coordinate of A, it will be 1 into I plus 1 into J plus 0 into K. This is vector OA because 1, 1, 0. So 1I, 1J, 0K. That is the vector OA minus vector OC. Coordinate of C is 0, 0, 1. So vector OC is 0I plus 0J plus 1K. This will be I plus J minus K. So this is vector R. So vector R is known. Now vector F. Vector F is 5 Newton force along the positive direction of y-axis. It is in the plane of xy axis, that is its height along z coordinate is 0. Hence its z component will be 0, and it's along the y axis and perpendicular to x axis. Hence its x axis component will also be 0. So f is equal to 5 into j, that you can easily find. Now n, what is n here? N is unit vector along axis of rotation. So along positive direction of z axis, unit vector is n is k. Now all three vectors r, f, n are known. Just put the values of these vector in this formula. R cross f, that is I plus j plus k minus k, minus k cross f, is 5j. So we are first finding r cross f. This term we are finding here. So this can be written as, we know a cross b is equal to minus b cross a. A cross b is equal to minus b cross a. So I plus j minus k cross 5j can be written as minus 5j cross I plus j minus k. So this is minus 5 j cross I plus j cross j minus j cross k. So this is minus 5 j cross I plus j cross j minus j cross k. This can be written as minus 5 j cross I. We know I cross j is k. So j cross I is minus k. J cross j is 0 and minus j cross k. J cross k is I. So this is minus I. So this can be written as 5 I plus k. So we have found r cross f as 5 I plus k. Now we will find r cross f dot n, where n is k. So 5 I plus k dot k, that is n. So this is 5 I dot k plus k dot k. So it is I dot k is 0, k dot k is 1, so it is 5. So we have found r cross f dot n. Now vector n, t is 5, that is r cross f dot n, into vector n is k, 5k. So I am again repeating this. This is the general formula. We have found r. R is by finding vector CA. CA, OA minus OC. Coordinate of C and A are given. So this is vector OA. This is vector OC. We have found vector R as I plus J minus K. Force F is along the y-axis in xy plane, so it will be 5J. And vector N, that is along the z-axis, axis of rotation, is K. Now RFN, these are known. So first of all we will find R cross F. R cross F, here R. So this is R cross F, I plus J minus K, that is R. I plus J minus K. So I plus J minus K cross F is 5j, this is 5j. We have just reverted it by A cross B is equal to minus B cross A. So it can be written as minus 5j cross I plus j minus k. After carrying out its operation, it comes out as 5 into I plus k. So R cross F, that is R cross F is 5 into I plus k. Now R cross F dot n. Here n is k. So R cross F is 5I plus k dot k, which is n dot k. So after dot of product operation, it will come only 5. So R cross F dot n is 5. So D is R cross F dot n into vector n. So n is k. So R cross F dot n is 5. So we will get 5k. So here also you can write torque is equal to 5k. So this is the third method, and this is by I, J, K. So here we have found torque of this simple force about z-axis with 3 different methods just for illustration and conceptual purpose. The example is very simple to understand. First of all, we have found the torque of F about z-axis by simple technique that a torque of a perpendicular force on an axis and not intersecting the axis is equal to perpendicular distance between axis and force into amount of force. That is T is equal to Rp into F. Rp is perpendicular distance between axis and force into force. So by this you will get torque is equal to 5k. Second method, by dividing force into in x, y, z directions, components fx, fy, fz. F is equal to fx plus fy plus fz. So by finding the torques of these individual forces, components of F about the same axis and summing them, we will get net torque 5k. And third method, by IJK, that is right-handed unit vector system. So in this case, we will find R, vector F, vector N, R, F, N in terms of IJK. After finding R, F, N in terms of IJK, just put these value in this expression. We will find the torque of F, that is this torque along the z-axis, which is also 5k. So this is the basic concepts behind this torque, and torque of a force about a point and about an axis is slightly different. Next is bending moment. For a beam, just take a simple example. So this all discussion will clarify your understanding about equilibrium. Let the force F is acting. Here reaction R1 and here reaction R2. Now bending moment. So this body is in equilibrium. About any point, we know in equilibrium, about any point, arbitrary point, total moment, total torque of the forces will be 0. So about this point, the moment of these two forces, for F it will be anti-clockwise, for R it will be clockwise, about this point. So it will have moment, the resultant of both these moment will be equal to moment of this about this point, because total moment is 0. That means if we cut the body, so left side forces are trying to bend this beam about this point with moment equal to total left side force moment or total right side force moment about this point. Again I am repeating, about this point total moment of R1, F and R2 is 0. But if you cut this beam from this arbitrary point, then moment of R1 and F about this point will not be equal to 0. Sum of both these moments, this is clockwise and this is anti-clockwise, about this point will not be 0, and this sum will be equal to moment of R2 about this point, then it will be 0. So these two moments of these two forces are trying to bend this beam about this point with torque equal to net torque of this and this force or equal to torque of this force, because torque of this is equal to torque of this and this. Total torque is 0. So only torque of this and this is trying to bend this beam about this point. There is a moment, net moment of all leftward forces about this point, and there is net moment of all rightward forces about this point. So if body is weak, material is weak, then this material will just bend. So either this beam will take this shape, or because of these forces this beam may take this shape also. So because of this bending moment on either side of the beam, the body will take this shape or this shape if it is weak. If it take this shape, this is called sagging moment. If the net moment at every point due to only leftward forces or due to rightward forces is such that it try to bend the body in this shape, then it is called sagging moment. If it try to bend the body in this shape, this is called hogging shape. So when the bending moment is nothing but it is the moment for any arbitrary section created by only leftward forces or only rightward forces, and both these leftward force and rightward force moments about this point are equal and opposite, and they are non-zero. So the net moment by only leftward about this point is called bending moment at this point, even though total moment of all three forces about this point is 0, but bending moment is moment created by only leftward or only rightward forces for a given arbitrary cross section. There is convention to represent the bending moment also. So at a point, the bending moment, we start from left side, and force which are upward, the moment due to upward forces about this point is taken positive, and moment due to downward forces about this point is taken negative. So again I am repeating, when you will take bending moment about this point, so we will only consider leftward forces, because if we will consider total forces, then net moment will be 0 for any point. So we will only consider one side forces. As per convention, we will only consider leftward forces. So about this point, to find the bending moment for all upward forces which are in left side, all upward forces, their moment is taken positive, and all downward forces on left side of this point, their moment is taken negative. We will sum up these positive and negative moment of all forces acting leftward of this cross section, arbitrary cross section about which we are finding the moment, and that sum is the net bending moment about this point. So now this is a beam AB. You can say it A. This is a beam and these are two supports. These are two supports. A force F is applied at point C. This is point C of the beam. A force F downward is applied on the beam at point C, which is located at length L by 4 from point A. The total length is L for the beam. Force F is applied at point C at distance L by 4 from point A. This is the remaining length 3L by 4. So we will draw bending moment and shear force diagram of this beam. So first of all, we have to find all the forces acting on the beam. We have to find the forces acting on the beam. To find the forces, we have to draw the free body diagram of the beam. So let us just draw the free body diagram of the beam. Assume beam as a system. So let a reaction force R1 is acting at point A and R2 at point B, and this is length L by 4, and this is 3L by 4. So for linear equilibrium, first equation R1 plus R2 is equal to F. R1 plus R2 upward force and F is downward. So this is for linear equilibrium, that is total external force on the beam is 0. For rotational equilibrium, just take moment about point A. Moment of all external forces about point A. This moment of all external forces must be 0 because beam is in rotational equilibrium. So moment of F about A is F into L by 4. It is in clockwise direction. And moment of R2 about A is in anti-clockwise direction. So both moments will be 0. That is R2 into L. R2 into this distance L in anti-clockwise direction and F into L by 4 in clockwise direction. So here you can say R2 is equal to, this can be cancelled, F by 4. As R1 plus R2 is equal to F, so R1 can be written as 3F by 4. So we have found these reactions. Now we have found all the external forces on the beam. So we can draw the free body diagram of the beam. This is the beam, this is point A, this is point B. Reaction at point A. Reaction at point A is R1, that is 3F by 4. At this point, F is acting, this is point C. And at this point, reaction F by 4. So this is the free body diagram of the beam, showing all the external forces and torques. So these are the external forces, F 3F by 4 and F by 4. So let us draw bending moment diagram. This is A, this is B. So bending moment diagram is nothing but it's a graph showing the value of bending moment at every point of the beam. So now we will find the bending moment. Bending moment, as we have told you earlier, that to find the bending moment at any point, just consider the leftward forces and find the net moment of all leftward forces about that point, taking upward force moment positive and downward force moment negative. So let us take an arbitrary point between A and C at x. This is located at distance x from A. So the point x is from A is at a distance x. So for this arbitrary point, leftward force is only 3F by 4. 3F by force is this force. So the moment of this force about this arbitrary force is 3 by 4 F into x. This distance x. 3 by 4 F into x. So when we will start from point A, then x is 0. So at point A, bending moment will be 0. And from equation you can see this is increasing linearly with x. That is, when we are moving towards C from A, x is increasing. So it is proportional to x. So the expression of bending moment between A and C will be linear. This is point C. So at point C, x is equal to L by 4. So put the value L by 4. It is 3 by 16 FL. 3 FL by 16 at point C. At point C, the moment of leftward force, that is 3F by 4, is 3 by 16 FL. So at point C, it will increase up to 3 FL by 16. This is the value of bending moment at point C. It is increasing from 0 with increasing the distance from A and reach the maximum value at point C, which is equal to 3 FL by 16. Now consider, because here another force has been inserted. So when you will find the bending moment for arbitrary points between C and B, you have to consider the all leftward forces. If you take this point, this arbitrary point, so leftward forces are F downward and 3F by 4 upward. So you have to find bending moment with different expression. So this expression is not valid for points lying between C and B, because between C and B force F has entered. This expression is valid only between A and C, where all leftward forces will be equal to 3F by 4. For all points between A and C, leftward forces is only one, that is 3F by 4. So sum of all leftward forces will be only 3F by 4 between A and C. Hence this expression 3 by 4F into X will be applicable between A and C only. Now take arbitrary point between C and B. So remove this expression which is not valid between C and B. So let us take arbitrary point this. Let this point is located at distance y. Distance y from C. This is just arbitrary point. To find the bending moment about this point, we have to find moment of all leftward forces about this point. Always remember all leftward forces, not total forces. If you will take total force moment about this point, it will be 0. So moment of only leftward forces will be equal to moment of rightward forces about any arbitrary point. So as per convention, if we take this arbitrary point, so the moment of leftward forces, there are two forces. One is this 3F by 4 upward. So the moment of this force about this point will be positive as per convention. So this 3F by 4 distance from this point is, this is L by 4 and this is Y. So the moment of 3F by 4 is 3F by 4 into L by 4 plus 5. Y is distance from C to this arbitrary point about which we are finding bending moment. So moment due to 3F by 4 is positive as per convention because this is upward force about this point. Now second leftward force for this point, leftward force is this F, which is downward, and its moment will be taken negative. So its moment is minus F into this distance Y. So after simplifying this expression, you can write it like 3FL by 16, 3FL by 16 plus 3FY by 4 minus FY by 4. So it will be minus FY, sorry, it will be FY minus 4, where Y is distance from C for arbitrary points between B and C. So you can see this 3FL by 16, this is the moment at point C. When we move towards point B, Y will increase and the total value will decrease linearly because it is proportional to Y. Hence the moment will start to decrease. Now where it will be 0? For which point it will be 0? So put this expression equal to 0. So by putting this expression 0, we can find Y is equal to 3L by 4, which is this total distance, 3L by 4. So after Y is equal to 3L by 4, that means we have reached at point B. At this point, total moment will be, bending moment will be 0. So it will be like this. So this is the bending moment diagram between C and B. Bending moment is given by this expression, that is by this expression, and between A and C, bending moment is given by 3Fx by 4 between A and C. So it is just a simple formula of moment. Here only you have to consider one side forces. So this is the value of bending moment at every cross section of this beam. So you can see between A and C at different points, bending moment is increasing and it has reached maximum at point C, which is equal to 3FL by 16. After point C, bending moment is given by this expression. So it has started reducing due to this downward force. So you can see after point C, the bending moment has started to decrease, and at point B, the bending moment has become 0. So in mechanical engineering, these diagrams are used to find the stress at different points of the beam, how much internal stress is created. Even though structure you may see it is static, tower is standing, bridge is standing, it's not moving, but actually different forces are acting at different part of the bridge, bending moment and shear force. These forces should not cross the strength of the material. The strength of the material should be above these internal shear forces and bending moments to overcome the bending moments. Only then structure will be in equilibrium and will be in rigid condition.